Hello, my name is David Scher. We're in Physics 572, Introduction to Health Physics. We're going to go over homework problems, and in particular, the ones that require competition. So I'm going to start by sharing my screen, and then we can start talking about this. Okay, let's go with that one. Okay, everybody see my screen? Okay.
I see it. Looks good.
Just want to be able to communicate to you and the rest of the world. We are recording or we are not? There should be a sign.
I see the red light.
Well, that means we are, because
Yes.
I'm at a different screen now. Now that I'm sharing, I can't tell. Okay. So I don't want to have to do this again for everybody else. Okay, so we're going to do homework 5, go over some problems of homework from unit 5, unit 6, unit 7, and the last lecture about counting statistics. I hope I can get through all this in a reasonable amount of time. There are a lot of questions that are narrative in nature. I've provided some comments in response to homework for people. I think those things you can look up, or you can ask me about them, and I'll try to explain. But I'm going to try to focus on the computational problems. Okay, so one of the problems we did in unit 5 was the problem said that if you have these several 3 MeV photons, they interact with 1 cubic centimeter of tissue, etc. And wanted to calculate the total Kerma. So what a number of people did was try to use the general formula for Kerma, and I'm going to try to get to the slides. Okay. Try to use the general formula for Kerma that was, let's see. Kerma is back here, where they had the where we it was the energy of the initial photon minus the energy of secondary photon divided by the initial photon times the cross section. That ring a bell to anybody? Am I in the right? Oh, that's the wrong class. That's why. Wrong folder. So this is not the one I want, but okay. Let me go back here and get the external symmetry. Okay, so we said that the Kerma is, you use all these factors, right? So you multiply the photoelectric effect by however much energy is, what fraction of energy is transferred, same thing for Compton effect, etc. For the problem we have, this requires some knowledge of what the mu's are, etc. And in the problem we have, where are we? We are looking for unit 5. So it just says there's 1 photon that undergoes this kind of transformation. There's 3 photons that undergo this kind of transformation. It doesn't give us the attenuation coefficients. So, and it's also an unusual mix. It's a little bit artificial. These may not have been the actual what would actually occur in a thing. The idea here was just go back to the definition of Kerma. It's the energy transferred divided by the mass. So that was the idea behind the problem. So just take each photon and figure out what the energy transferred is. For a photon that undergoes photoelectric absorption, then all of the energy is transferred. For a Compton scattering, and with a particular angle for 90 degrees, then you use the formula that was in that we learned about how much energy is transferred to the electron from Compton scattering. It's back to the basic definition. And there's 85% of the energy is transferred with a 90-degree scatter with a 3 MeV photon. Straightforward. For pair production, it's the energy minus the mass that's created, the electron and the positron, 2 × 10⁵ So rather than using that other formula in terms of the coefficients, we can't really do that for a problem that's set up this way. This was set up just to use the principle, the idea of the definition of Kerma. It's the energy that's transferred. Figure out how much energy is transferred for each interaction. So I buzzed through this pretty quickly, but let me, the one that's most complicated is the Compton scattering one. Does everybody remember? Well, I'm actually recording for people who aren't here, so I shouldn't ask. In Compton scattering, we had the let's see if I can find the formula. Yeah, it's not there. This is not working for me. How do I get out of here? Oh, there it is up there. In Compton scattering, it's this equation, right? This is the energy transferred to the electron divided by the energy transfer that's from the initial photon. Okay, and with cosine is equal to 90, or when theta is equal to 90, cosine theta is 0, so that made it a little bit simpler. I think that's why the 90 degrees was selected. Okay. So there were three. There was one photoelectric effect, and that has a ratio of 1. There were 3 that transferred 85% of their energy from Compton scattering, and 2 photons with pair production. And it turns out that 66% of the energy is transferred in Compton scattering. That's 66% is the 3 MeV photon minus 1.02 MeV energy produced divided by the 3 MeV of the original photon. Okay, multiply all that out, 14.6 MeV is transferred from those set of 6 photons. The mass is 1 gram, assuming it's 1 gram per cubic centimeter. And so the Kerma from all that would be 14.6 MeV per gram. You didn't have to do it. The problem didn't ask for it, I don't think, but I converted it to SI units. And it turns out it's 2.35 picogray. Okay. Is this clear on how we set up the problem and the logic for doing it? Like I said, this was a little bit didactic. I can't imagine that you would ever know that there was 1 photon that interacted in this way and 3 photons that interact in the other way. It's just the way the problem was set up.
My only question is on my homework, you had a note. How did you get the XCOM data for tissue?
Right. So let's go to XCOM. Yeah, let me show you. You have to put in a formula to use XCOM.
Uh-huh.
So I'll tell you what, I'm gonna leave this over here and it's going to share a different screen. So I'm going to share my screen 2. So if I go to XCOM 3R or XCOM NIST, not MIST. Okay. So you would have to do a mixture, right?
Mm-hmm.
And what would you put for the elements? You know what I'm saying? Did you just use water?
I think I did just use water.
Yeah, it's probably not very far off. But if
Uh-huh.
you know what I'm saying? So let's go back and do it with, you could do it that way. The problem with it is, as I said, also is, in reality, I don't know that there would be one photon interacting this way, three photons interacting that way. That was sort of artificial. Now, I'll confess something I maybe shouldn't say. These homework assignments, I'm using the same homework assignments that were uh, uh, used in the past, because a lot of this has got to be used as preparation for the qualifying exam. When people do the qualifying exam, I tell them, look at what you did in 572. And so I need to preserve some continuity for that purpose. Does that make sense? So I
Is qualifying exam the same thing as the comprehensive exam?
comprehensive, sorry, you're comprehensive. I'm sorry. Qualifying exams for PhD, comprehensive exams for masters. But yeah, so I need to preserve some continuity so that everybody has a similar experience to get ready for that.
Okay.
So that's why I'm using these. I wouldn't necessarily have chosen to sort of artificial or art, yeah, just for didactic purposes, if that makes sense to you.
What was
Am I
the
sharing? Oh, let me share that screen now. So
what was the other option? What would you use instead of water?
well, you can go to ICRU. There are formulas right there.
Oh, okay.
So you could, use what you have to find the least common denominator and make it all work, right?
Okay.
But there are, yeah. So this is probably, that's good. People are learning. This is not something a practicing health physicist would use, but people who do these kind of calculations for, deriving standards and that sort of thing have used this kind of information to, these approximations to tissues. That makes sense to you?
Yeah, no,
I
that's
don't
good to
expect
know.
that you would have known it. That's what I'm saying. And the reason I asked the question is maybe you did know it, and you could write back and say, of course, I use the ICRU 4-element formula.
Sure.
Okay. Okay, so I'll go back to the and yeah, okay. So that tells you, so basically in this problem, we're using the basic idea of energy transfer divided by mass, figuring out what the current is that way. This one is more of a nominal problem. It's not really a calculational problem. Just have to look up the correct attenuation coefficients and divide them and figure out why they're people. I think most people gave good reasons as to why the attenuation and energy absorption coefficients are different. It's got to do with energy that escapes, that's not carried away by charged particles. So it's from Compton scattering, it's from bremsstrahlung, it's from annihilation radiation. It's energy that's carried that is lost from the photon, but not imparted to charged particles. So basically carried away as by other secondary photons. Okay. Define Rankine. So this was one, calculate the air kerma for 37 megabecquerels of cesium-137 or a millicurie. Now, a lot of people calculated what the exposure rate is by looking at the energies of each constituent part, and very similar to what we do in problem 3.
Sorry. Do you have your screen up? I can't see the screen.
Oh, am I not sharing the screen at this moment? Let me figure it out.
I don't know.
Yeah. No,
I don't know
you
if
would
that's
know. I can't tell whether I'm sharing or not. You can tell better than me.
I'm not very good at Zoom. There we go.
Okay. So this problem was calculate the air kerma rate at a meter.
Uh-huh.
A lot of people did like what we do in question 3. They figured out what the activity is, figured out what the photons energies are, what the absorption coefficients are, etc., and did it that way. For this problem, I think I thought it was acceptable to just use the gamma constant. I think I gave you a table of gamma constants so I just went to that table, the one that it's from Health Physics by Peplow. Looked up what the gamma constant is. The gamma constant is the dose delivered at 1 meter from whatever the specified amount. They said it's 8.25 10 to the minus fifth milligray per hour per megabecquerel. Okay, so I just multiplied by the 37 megabecquerel to get the dose rate at 1 meter in milligray per hour. Okay, and so that was the whole question. What is the dose rate of the meter? Now, I added an additional element here. It's nice to check your answers. Did we? I believe in this class we covered a rule of thumb, or I hate that phrase. A typical rule that the dose rate at a meter is 1/2 times NCE. N is the number of photons, C is the activity in Curies, E is the energy in MeV. Alex, are you familiar with? Have you heard of this rule before?
Yeah, I've heard that. I didn't know it off the top of my head though.
Yeah. Did we not cover that in one of the anyway? It's a good way. It's a simple formula. It's a good way to check yourself. That's all I'm doing is check my answer for reasonableness. And so I use NCE, and that N is again the number of decays, C is the activity in Curies, E is the energy in MeV, multiplying together, and it turns out to be very similar. The approximation is 3. Well, it's R. Well, yeah, that's in R per hour. So I had to change it to the SI units. It's about 3 times 10 to the minus 3 milligray. That's what I had before, was 3 10 to the minus 3 milligray. So that gives me confidence that I had the right answer. That's the only reason for adding that step.
Gotcha. That's good to know.
And that might be a good idea for people, just to the audience in general. It might be a good idea, and if you have time, to verify that you're in the right order of magnitude. So a lot of the answers I noticed were off by 3 orders of magnitude, or some because of some simple math error, right? Getting the exponents wrong, calculator problems, whatever. So if you have time, you have these little rules of thumb. It's worthwhile to double check to see if it's even reasonable that you're in the right magnitude. Okay, so for problem 3, we're asked for, we have a 5 milligram cesium-137 point source, and what's the activity? Most people understood that use this by this formula. It's related to specific activity. It's the activity times Avogadro's number divided by the molecular weight, and then multiply that by the mass. The activity times Avogadro number divided by the molecular weight is the activity per gram. So multiply by the mass in grams, and you get your answer. But that was, I think many people understood it. So this is something we did back when we were doing a review of radioactivity. Let's see. So we need the parameters that are in that formula. The decay constant is the natural log of 2 divided by the half-life. The half-life is, I went to the HPS website and saw it was 30.04 years. Then I converted it from years to seconds. I want to have consistent numbers across the board. In fact, it asks for units in becquerel, so that means I need to have lambda in 1/seconds to get that right. So that's what I got, is lambda in terms of seconds. Stick all the numbers in, the lambda that I calculated from the 30-year half-life, Avogadro's number is right here, 6.02 times the mass, 0.005 grams, 5 milligrams. Then divided by the molecular weight, it's about 137 to the accuracy we have. 3 digits is good enough. And multiply it out and get what we want. Then I had to convert it to traditional units because that's the problem it asked for, becquerels and curies. So I had to make sure that the units are per second. They all worked out to be per second. The moles canceled out, the grams canceled out. I ended up with just per second. So for the activity, I have the activity in becquerels, and then 1 curie is 3.7 times 10 to the 10 becquerel. The definition, it comes from the activity of 1 gram of radium. And so it was 0.435 curies. Most people got that, I think. But if it no problem if you didn't. I just want to go over this so you can see how the logic I went through. So it's a matter of remembering this idea from the specific activity and then doing the math correctly and then the conversion. When you have to do conversions, it's not that hard to find them on the web. So what I might do is just simply put in a Google search. I think you actually do it with symbols, BQ2CI, and I find definitions all the time. I'll find calculators as well. So that's a little trick for an online course. You always got an internet, a computer with you, so it's not hard to look up conversion factors. Okay, so the next question is, with this activity, this many decays per second, what's the flux? The flux is the number of photons emitted divided by 4 pi r squared over the whole area of a sphere. Now, some people forgot that when it's not just the number of decays per second, you have to multiply by how often a photon is emitted. So if we go to our HPS decay data, and we go to, this was cesium-137. Yeah, cesium-137. I go to cesium-137. It decays by beta 94% of the time to this energy level. And then it says, that also decays from barium-137 metastable. So the cesium decays 95% of the time to barium 137M, and then barium 137M gives off a photon 90% of the time. So 94% to the of the time it goes to beta, and 90% of those betas produce photons. Overall, it's 85% of the time a cesium-137 decay gives me a beta particle. So that's why I got this 0.944. That's how frequently the beta occurs. 0.91 is how often a photon is emitted in that daughter product. And then I divide by 4 pi times, this was asked at a meter, right? 10 meters, right? Is that what we? 1 meter. So we've got to divide by 4 pi r squared. Well, r is 100 centimeters, and so square that, you get 10,000, whatever it is. And this should be 100.0, typo, but it turned out to be 1090 per square centimeter per second. If I multiply these out. Okay, so that's the logic I use for that. The trick is to remember the yield per decay in this. Okay, calculate the air Kermer rate. This is how some people did the previous problem. It's the flux that we just calculated times the energy absorption, mass energy absorption coefficient. I went to the database and NIST. So where is my? Let's see. went here to NIST. I went to, this is for air, so I needed to go to compounds and mixtures. And this is wrong. I made it wrong. That's the data. Okay. So I went to air. And so we have an energy of 662 keV, 0.662. So I took the value for 0.6 and the value for 0.8, and I interpolated between them. It's probably close enough to just use the average between 0.6 and 0.8. That would be 0.7. But I did it. It's just a little bit of algebra. So I take the value at the lower energy, the value at the higher energy, subtract them, and then you divide by the difference. It was 0.2 MeV in this case, right? That's where the 0.2 comes from. That's the slope. Multiply it by the value I want and add. This is mx plus b, and that gives me the new value of mu that I want. Is that clear, or should I do one of those on the board here?
Makes
Let me
sense to me.
So here's what we had, okay? At 0.6, the value was 0.2953. At 0.8, it's 0.0288. Okay, so the slope is equal to, this is going to be y1, y2, that's it, right? That's the slope for between them. So I've got 0.6, 0.8, and I've got two y values. So then I say y that the new y I'm interested in is m times x minus the x I'm interested in, x, pick one. Right? That makes sense to you?
Yeah, makes sense.
Okay, I think
Yeah,
I might
what you're saying makes sense. A question I have though is that truly linear? Because I thought
it's not,
overall
but
it
it's the
should be
best.
linear or
It's not.
exponential.
It's not linear, but it's the best estimate I can do without going to heroic. You know, a linear estimate is going to be closer than choosing either endpoint.
That makes sense then.
Yeah, the actual graph is something like this, right? Right, but this is closer than using either of those. So it's just a better estimate than just picking one. And again, points, given the magnitudes of errors here, picking 0.7, just using the average of 8 and 6 and 8, 0.7 is close to 0.66. And that's probably the way I did it is probably not going to yield any difference that's meaningful. But I did it before I thought of that. Okay. So let's go back to share my screen. So this is just a linear interpolation. It's and that gave me this 0.231. Actually, since we're doing it, it would have been 2918, and if I just did the average between them, and I got 2931, so it's very close to the same value. Anyway. Okay, so now I've got this formula. It's the fluence times mu n over rho. I figured out what mu n over rho is. The fluence we calculated up here is 1090, and times E, which is 0.662 MeV. That gave me 21.15 MeV per grams per second. Okay. Was that the end of a problem? I can't remember. Well, I converted it to other units besides MeV and grams and seconds. So the 1.6022 E minus 10 converts from MeV per gram to joules per kilogram. It includes, so the conversion from MeV to joules is 1.602 10 to the minus 13. If you go all the way to EV, it's 1.602 10 to the minus 19. And then converting from grams in the denominator to kilograms gives me a factor of 1,000. And that's how it came out to be 1.602 times 10 to the minus 10. It's a amalgamated or accumulated conversion factor. There was some confusion by a few people. That's part of where we ended up being off by orders of magnitude. They used this number and then also converted grams to kilograms. So yeah, I will tell you that it takes a long time to find out where people made these oversights. It takes an hour to grade some of these homework assignments, just trying to find out where that misstep was. But what I'm using here with these primes, this is a dose rate. This is the air Kerma rate. So I use prime because I can't put a dot, which is a traditional symbol for time derivative. I can't do that while I'm typing, so I use the prime, and that's what I calculated it to be. So then I said, let's check this answer with the previous result. In the previous result, we said, what is it for this source? What's the activity at a meter? And this was the second one is at 10 meters. So I just took the previous result, scaled for distance, and I got an answer that's comparable to the answer I calculated. Okay. And that is why it's 1,000. This is at 10 meters. The flux at 10 meters. That's why it's 1,000 centimeters, because that's what it is for 10 meters. I said it was a typo, but it wasn't a typo. Everybody good?
I'm good up to this point. The question that I have, I think, is more of a conceptual one.
Yes.
So we've talked about Kerma,
Right.
and then we've talked about air Kerma.
Right.
And right now, I guess I'm not distinguishing the difference between those two.
Right. So you can have Kerma in tissue. How much energy is being released in tissue? You can have Kerma in any material. Air Kerma just means the material we're looking for the Kerma in is in air.
Okay.
So we're using this mu en from air, not mu en for lead, not mu en for concrete, not mu en for tissue. When we talk about air Kerma, we're looking at what is the energy that's imparted in air.
I think that answers my question.
Okay.
Thank you.
Well, I think we finished the first one. If I have any questions about this, let's try to hit them now. Otherwise, I'll move on.
If I can, I want to interrupt a little bit.
Please do. Anybody, anytime.
So I was going through my notes and looking for the homework, and I thought that I was well organized. The homework that I had printed out was different than the one that you went over. But yet I had the work, so I remember going over those problems and doing them.
You did them. You turned it in.
Yeah. But I have a printout that says Unit 5 homework, and I wonder if it was Unit 6, and maybe
possibly because I renumbered some of the units that we did. So
are we going to go over Unit 6 next?
We're moving on. Is this the one you saw? Is the one that says unit that you got about committed dose and that sort of thing?
That's it.
So I'm
Oh.
sorry about the misnumbering for whatever reason.
That's okay. Now I know where to, I put it in the wrong folder and I thought, well, is this for the other class that you
Nope.
teach? I
Nope.
didn't know.
You now we got it. I'm sorry if I contributed to confusion there. Okay. So the first question in this in the Unit 6 homework was a conceptual one. So the idea of committed dose is that we're not we're counting future dose at the time it's delivered. That dose is committed because it's unavoidable because of physiology. That material, long-lived and long-retained material, is going to stay in you for a long period of time, and we count all that dose from the moment that the intake occurred, instead of counting it through time. That's what basically what committed dose is about. It's most useful for calculating effective dose or dose equivalent, effective dose. But it can also be used for organ doses too, which are, committed doses not added up for the whole body. So if I want to know what is the dose of the thyroid, I can talk about a committed dose to the thyroid, or a committed dose, the one we do about radium, where we have a very long half-life. I think it's in this assignment. You can have a committed dose, even though it's not used, even if you don't use it as with a titulating factor to get the effective dose for the whole body. So we can have committed doses for organs. We can have committed dose equivalents. They originally came up with the idea so that they could do effective doses, but it's used for organs as well. Okay. I noticed that in a lot of people in their comments, they said that committed doses is used for effective dose. It is, but it's not only used for effective dose. That's why I'm mentioning it here. Why are the DAC values in the NRC different from the DOE? This is again narrative. I don't really want to spend a lot of time on the narrative issues. Largely, a lot of it is because they were based on different assumptions. They were adopted at different times. The NRC adopted their approach around 2000. Well, no, about the 70s. And they've lived with it since then. They did not adopt the updated rules. When ICRP issued new standards, they didn't change with the standards. The DOE did change to the new standards, and so their rules reflect different fundamental the different fundamental assumptions. The tissue weighting factors are different. The NRC uses a Q value. The DOE uses the radiation weighting factor, so they have different values, and so the results are going to be different between the two different tables. Interestingly, the DOE rules don't specify alleys at all. They only specify DACs. So it's not hard to. So if you look at 10 CFR 835, there are no alleys listed in them, only DACs. You can back engineer and find out what the alley is, but that's just not in their rules. And it makes sense, because if you're worried about occupational exposure, almost all of that is inhaled. People don't eat radioactive material at work. The ingestion values are more useful for the public exposure if there's some environmental contamination and then they eat contaminated, foods that were accidentally contaminated. Then that's when ingestion more often occurs. It's not a common occurrence in an occupational setting, and the DOE is primarily concerned about occupational, not about environmental issues. That's EPA and DOE's, NRC's main interest. They're the ones most interested in that. Okay, so there are other minor differences. For example, the particle sizes that are used that are part of the assumptions. Okay, I asked you to write about Alexander Litvinenko. It's a long story from the many years ago now, but I think everybody was able to find the information and write it down. Let's do some calculations though. Intake of 0.1 milligrams of radium. It's the model of the radium girls. So we talked about the radium dowel painters that occurred. We did talk about that in this class, right? So when that work was done, they came up with, and this is the 20s or pre-war anyway, they came up with the standard ought to be less than ingesting less than 0.1 milligram of radium. That should be the body burden for radium. And so that this problem we're doing has some historical value or historical precedent. We're calculating doses that would be due to the standards that were developed at the time. Okay, so about 20% of what is taken in by mouth enters up in the blood, and all of that enters up in the bone. And we have a number for the bone mass. We have a source that we were asked to use for elimination and decay data, and then we can get the charged particles, the data from our HPS website. Okay, so what's the initial activity? I took a shortcut. Some people went through and did the calculations. The shortcut I used is that this is radium, and the definition of the curie is based on radium. So 0.1 milligrams is 0.1 millicuries. And so that's how I did it. I just used 0.1 millicuries because I knew what it was for radium. Some people did that same calculation we said before, specific activity. When people did that, there are a few people who used the effective half-life. When you're calculating a radioactive activity, you can't use the biological elimination as part of that. You have to use the physical half-life, not the effective half-life. But I, again, took the shortcut and just said this is radium. So I know it's a gram is a curie. So this is 0.1 millicuries. And then the uptake fraction is 0.2. And so there was 20 microcuries in the skeleton. I multiplied that by 37 megabecquerels per millicurie or 37 kilobecquerels per microcurie, and got what the activity is. Okay. These are the half-lives that we were asked to use. It's a matter of looking them up. I think everybody pretty much was able to follow the link. Now, then the question is, calculate the absorbed dose in the skeleton as a function of time. This is not really absorbed dose. This is an absorbed dose rate as a function of time. It's a misnomer. I should have corrected this. The question, when we're calculating this, what we're calculating is a dose rate as a function of time, right? So if you look at the units, I've got K, F, E, A over M. Now, the A is got units of per second or per whatever. It's units of per unit time. So the overall quantity at the end is going to be per unit time. You know, micrograys per second, micrograys per hour. Now, a lot of people did these calculations in seconds. I did them in other units. That's fine. First thing we had to do is figure out what the decay is, the energy of the charged particles. So we go to our HPS website. We look at radium-226. Radium, there we are. 226. There are a couple of alpha particles. Those are almost all of the energy. One of them occurs 95% of the time. One of them occurs 5% of the time. 94 and 6, whatever. So that's what these are. This 4.6 is 5% of the time. This 4.7 is 95% of the time. And average those out, and I get what the dose, what the decays, how much energy is being deposited per decay. Now, I also went back, in addition to alpha particles, after the alpha particles are emitted, the atom is still giving off Auger electrons and X-rays and all that, conversion electrons. And so I added these in. It ends up there are more particles. There's more than one particle per decay, but that's okay. That energy is being deposited in the tissue anyway. So I just put these into a spreadsheet, copied this all over, multiplied by the energy times the frequency, and then added that all up. And I got 47.79. So it's a very small fraction in addition to the alpha particles. Very little additional energy is being deposited by those electrons. And if we were going to do equivalent dose, we would multiply this by a radiation weighting factor, which would make this even more important for the alphas and less important. We're only doing dose, we're not doing equivalent dose. So I added them in anyway. Okay.
I know you made Daniel very happy, including the 1,000th digits there.
Yeah. These I just copied.
Well, yeah, just for the
He had way
For the-
more
for the
digits
electrons.
than this. He had way more digits than I've got. He is the spreadsheet king. Okay, so we got our mass. So the formula for the dose rate is this K is the thing that converts MeV per gram into gray joules per kilogram. That's what that constant is. It's 1.6022, 10 to the minus 10. Okay. Now the F1, many people put in 1 because when we did tritium, the F1 was 1. F1 is not the number of photons that are absorbed locally. F1 is this fraction, the fraction of intake that ends up in the body in the serum. That's what the F1 is.
That's not double counting it.
Well, no, because when I did the formula, where are we at here? We're down here. Where am I doing it? It's right here. The activity I used was not, it was the original activity, the intake activity.
Okay. Gotcha.
I did not use the 0.74.
I think I just did it the other way.
Yeah, it's okay to move that F1 and to use, and to me, it shows that you're thinking along what's happening, that this is the energy that's in the thing, but then you shouldn't put the F1 in the formula. It's over in the activity. You know what I'm saying? It's demonstrating it's conceptually. I don't think I took any points off if people had it there. I want to emphasize here, not for purposes of grading, but for conceptually to understand what's going on. This formula, the F1 is how much is transferred from the blood to the from ingestion to the blood, or inhalation to the blood, intake to the blood, and then the A is the activity that's intake, not the activity that gets retained.
Gotcha.
For this calculation. Anyway, so it's the conversion factor for units, and then the activity that's in the tissue divided by the mass, and then it's a function of time. The activity is right here. It's the initial activity times the 0.2 e to the minus lambda t. That's what this is a function of time. So I calculated lambda somewhere around here. Oh, we did it, but it's actually just a given value. It's this value right here. I didn't have to calculate it at all. 0.693 divided by the effective half-life. Another key thing, and everybody I think got this right, for this formula where we're calculating how long how the energy is being emitted, we're using the effective half-life. We're not using the physical half-life at this point, because the material is being eliminated by decay, but it's also being eliminated by metabolic washout. Okay, so I just did a little bit of math, did this calculation here. I got 6 times 10 to the minus 8 grays per second. A lot of people stop there. I converted it to grays per day by seconds per hour and hours per day. And so the formula I got was 5.23 milligrays per day times e to the minus lambda t, and it decays away with time. Okay. I think that's how we did that problem. I hope that I've made it clear how you go about setting up these problems and the thoughts that go into it.
Back to
said,
the part A again, when you said you're not using the effective half-life, I'm just still trying to conceptually understand.
Okay,
it,
so
just because
what,
the blood is
I'll
fast.
try to hit on it. So when we're figuring out activity, activity is only the materials being decayed away by physical decay, by radiologic process. If it's washed away, that doesn't change the activity level. That is how many millicuries you've got. Does that make sense? So if we're trying to figure out how many millicuries, how many microcuries, how many becquerels we have, the only thing that we're including in that is the physical decay. The fact that it's washed out of your body doesn't create a higher activity. So a short half-life is
Yeah, that
associated with
makes
high activity, right?
Okay.
that make
Could you
sense?
also just say we're discounting biological half-life because it's T equals 0, you know?
Well,
didn't
you
have
can do that
time
as
for it
well. Yeah, there is no elimination at a given moment. But
Yeah.
when we're trying to assess what is the activity of this sample, based on the number of the amount of mass, then that having it washed away doesn't increase the activity, if that makes sense.
Yes, thanks.
Okay. Let's see, where are we? Initial activity we did with the half-lives. Oh, we were down here, and I said I just for the function of time. Now we're getting to what it is for a 70-year committed period. We use 70 years because as a member of the public, when we talk about workers, we use 50 years. So we're integrating this. This is the decay rate, or the dose absorption rate, how many graves per day. It's changing over time, and we're adding all those up for 70 years. When you do the integral with an exponential, it puts this H0 over lambda t, or lambda in the numerator, and it's this 1 minus the exponential. That's the result of doing that integral. Okay, here's where I calculate lambda e, because it's what we had were half-lives. So it's and I'm making it okay. So this is what's in the exponent, lambda e times 70 years, right? So the lambda e is ln2 over the effective half-life. It is being washed away. That's important for this purposes. And then I multiply that on a per day, so I multiply by the number of days, and I find out what's in the exponent. It's 1.77. So the amount that's decayed away, e to the minus lambda for that many half-lives, is 31%, 30.8% of it is washed away. That means all of this is 69.2%. I hope that I haven't gone too fast. I think this makes sense. That's just how I displayed the data when I did these calculations. So back here, H70, the 70-year committed dose, is H0 lambda. That's what the decay rate was at time equals 0. Then times divided by the effective decay constant, which is this, and then the 0.692 is this 1 to the minus e to the minus lambda t. That's 0.692. And so that's where these factors come from, multiplies out to 78 gray. Okay, does that make sense? Well, it's 5 milligrays per day, and it's over 70 years. So at the initial activity rate, 70 times 365, that would be 25,000 days. And if we just take our initial activity, which was 5.23 times 10 to the minus 3, If there were no decay, it would be 130 grays. So 78 grays makes sense. I'm in the right order of magnitude. This is just another example of doing a sanity check. I just took what is the initial activity? If there was no decay, or initial dose rate, if there wasn't any decay, what would it end up being? And then it's, you know, a few times more. It's 70% of that value is what ends up being the right answer. Okay. Okay. This is another problem we had to do. Someone is exposed to a soluble strontium 90, and there's a given air concentration. So a lot of people did this. There are a couple ways to do it. A lot of people did it by taking the air concentration, multiplying by the breathing rate, getting what all the intake is, and comparing that to the alley. Yeah, first I said find the inhalation class for this. So let's go back and let's do that. Let's find NRC. That's not what I want. I want this one. I'm going to go to, actually I can just use one of these. I better not. I want to show people how you get to this data. Appendix B has the data. So when you go to Appendix B, it tells you get the list of nuclides. I go to S for find strontium 90. Okay, and it's not now. Okay, so I'm looking at inhalation. This is for strontium 90 inhalation, and it says for D class C strontium 80. It's always the first entry per nuclide because the clearance class depends on the chemical form, not on the radiological properties. So all the strontium is going to have the same clearance classes. It says all soluble compounds are D class except one that has titanium, etc. So this is a soluble. The problem said it's soluble, so it's class D. Now I go to strontium 90 to get my value. And here are the alleys that are involved. Now, when you look at this and you see it has a tissue component, right? Bone surface, it's telling me that 20 microcurie is the alley. 20 microcurie intake leads to a dose of the bone of 50 rem, committed dose of the bone of 50 rem. The ones in parentheses are for the whole body. If there's no tissue noted, then it's for the whole body. It's for the effective dose equivalent. Okay. Interesting thing about strontium 90 is the value for the bone is equal to the value for the effective dose. So we have two ways to go about doing this problem. One is the effective dose equivalent, and one is with the organ dose. Okay. If you look at 10 CFR 835, and you look at the tables there, the table that they have for DAC is Appendix A. And if we look at strontium 90, the way it works here is for F class, they don't have D, they have fast, medium, and slow. They have one value, and they tell you that's bone surface. 1E minus 8 is the DAC. These are DACs, derived air concentrations, and it's bone surface. They don't tell you what the stochastic DAC is. It only have one standard to go by. It turns out that for slow, the standard is based on stochastic risk. Okay, so that's how the two data sets are different, or one way they're different. In the NRC world, it will always have a value for the stochastic, even if it's got a more restrictive value for an individual organ. Notice also that the values are different. The dose in here, the DAC, the air concentration for strontium 90 is 1 times 10 to the minus 8 micrograms per ml. The DAC is 8 times 10 to the minus 9. So a little bit lower in the NRC world. And that's got to do with the assumptions that were involved in creating it. Okay. So let's go back to the problem now. I've showed you how to look up the data you need. We find out that what the alley is, and I didn't write down the value, but it was 20 microcuries. We just saw it. And so we know that it's class D. Now, this again, the problem is a little confused. It says full-time and 1,000 hours per year. So I just did it with 1,000 hours. I think everybody else did it with 1,000 hours and discounted the characterization as full-time, which was probably the best way to go about doing this. So the concentration is 3 times 10 to the minus 3, 5 times 10 to the minus 3 microcuries per cubic meter. You've got to convert that to microcuries per ml to compare it with the DAC. And so the way I solve the problem is using DAC hours. So the concentration they're exposed to is less than a DAC. It's 5/8 of a DAC, right? They're exposed to 5 times 10 to the minus 9. The DAC is 8 times 10 to the minus 9. So they're exposed to 5/8 of the DAC for 1,000 hours. Multiply that out, and it's 625 DAC hours. Right? 0.625 is 5/8 times 1,000 hours is 625 DAC hours. Other people did this problem by taking the concentration, multiply it by the breathing rate, 20 liters per minute, figure out how much breathing takes place in 1,000 hours and what volume that is, and deriving what the intake would be under those cases. That's fine. You can do that in the NRC world. You can't do that in the DOE world because there is no alley. In the DOE world, there's only a DAC. So in the DOE world, you're pretty much limited to using the DAC hour method. You take the concentration they're exposed to, divide it by the whatever the DAC is in the table, multiply it by their time, and they get a DAC hour. Now, if this is a stochastic exposure, if this is the whole body, if this is for the effective dose equivalent, 2,000 DAC hours is equivalent to 5 rem. If it's for a particular organ, 2,000 DAC hours is 50 rem to the organ. So I had my 625 DAC hours. If I'm figuring out the committed effective dose equivalent for the whole body, I say 5 rem is 2,000 DAC hours. I was exposed to 625 DAC hours, gives me 1.6 rem for the committed effective dose equivalent. If I'm only interested in the critical organ, the committed dose to the critical organ, 625 hours, 625 DAC hours times 50 rem for 2,000 DAC hours, it would be 16 rem to the bone surface, 10 times as much. Okay? So you've seen the method here. It's interesting that when people calculated it by figuring out what the alley is, multiplying by the breathing rate and all that, they ended up with 1.5 rem effective dose equivalent, or 15 rem to the body. And that's got to do with all the rounding errors. Notice that these DACs and alleys are only presented to one significant figure. So it's not legitimate to give results that are more accurate than 2 significant figures at best. So Daniel, you probably don't want to give DAC hour or internal occupational exposure values with multiple decimal points. Okay, I probably shouldn't make fun of people who aren't here. Okay, but that's how I did it. And I hope I've made it clear. The other approach to solving this problem, the breathing rate is specified in 10 CFR 20 in 10 CFR 20 in the footnotes for this table. One more back, I think. When you go to the table, it tells you here what the breathing rate is. So if you don't remember, you can go here and figure out what the breathing rate, look up what the breathing rate is used. It's 20 liters per minute is what the breathing rate is. Think about the lungs and how many 20 breaths a minute and all that, and it makes sense. It's one way to remember it. Okay, so I've done so 16 rem for the bones and 1.6 rem for the committed effective dose equivalent. Now, we have another table, so we're going to look up what the doses are. We were given, I believe, the first 3 columns. We're supposed to come up with the last 2. Okay, so we have an absorbed dose, and we're supposed to find out what the equivalent dose is. In the NRC world, we multiply the absorbed dose by the quality factor. This is 10 CFR 20. That's the NRC world. We're multiplying by the quality factor. For photons from cesium-137, quality factor is 1. Beta particles, the quality factor is 1. So the equivalent dose is equal to the absorbed dose. For radium-226, it's due to alpha particles. The quality factor for alpha particles is 20. So I multiply the absorbed dose by 20. The thyroid, it's gammas and betas, so the quality factor is 1. For neutrons, 2 MeV neutrons, the quality factor is 8. And how did I get the quality factor is 8? Let's go to 10 CFR 20 and full text version. And I'm going to say, Control F first. There's a table with all the quality factors. There it's right here. So neutrons of unknown energy, it's 10, but there's a table here by energy. We had an energy of 2 MeV. So if I look here for 2, this is energy in MeV. If I look for 2 MeV, it's a factor. It's now I could have used 8, I could have used 9. I wouldn't count you wrong if you use the unknown energy as well. That would be fine. But that's what I use a quality factor of 8 based on that table. Okay. In the NRC world. Effective dose, I have to multiply by the tissue weighting factors to get the effective dose, right? So the effective dose is defined as the equivalent dose times the tissue weighting factor. What are the tissue weighting factors? They're also here, right here. And we're looking for the tissue weighting factor for liver. Well, we're looking at the tissue weighting factor for all of them. So we have red bone marrow, it's 0.12. We have breast, 0.15. We have lungs. It's lung is 0.12. We have thyroid. Thyroid is 0.12, 0.03. Thyroid is 0.03. Yeah. Oh, I did it wrong. Oh well. I marked me off. It should be 0.03, not 0.12. If I had a transcription error. And for liver is remainder. So for remainder, you take the 5 organs and give them 0.06 each. So no organ can have higher than a weighting factor of 0.06. Notice that in the NRC world, they do not include skin or lens of the eye in determining committed dose equivalent, the effective dose equivalent. They're just not counted at all. So I can go back here.
And just be clear by that, that's basically the same as saying the tissue weighting factor for like lens of the eye is 0.
Yep.
Okay.
In terms of, it has a separate standard.
Yeah,
So it does not get included in this at all.
All right.
Okay. DOE world, the DOE has its own tissue weighting factors. And that may be why I was wrong. But anyway, let's look at it quickly and go to 10 CFR. So if you go to the part 835, I think it's under general provisions. You can find the tissue weighting factors and the radiation weighting factors here. These are the radiation weighting factors. We have neutrons of energy 2 MeV, so the factor is 20. Okay. Was it 2 MeV? Is that what we were working off of? I've already forgotten what the problem called for. Yeah, 2 MeV. So did I lose something? Oh well, I closed my, oh no, here it is. We are doing that one. Okay. So anyway, I went to 10 CFR and got here are the tissue weighting factors. Okay, so that's where I found the tables and just trying to show people how you get the data so that you can do the problem, depending on which system you're going to use. I let people use either. If on a test, I might specify one or the other. On a test, I might give you the weighting factors to use. Particularly if it's like a comprehensive exam where it's closed book, closed note, timed. The tests I'm doing with you guys are not that way. But those are how we did this problem. Do I have any questions? Oh, and to get the TEDE, I add up all the effective doses to get the TEDE. That was one of the problems that one of the things was asked for. Calculate total effective dose equivalent. Here it is right here. Okay. Now, should we move on to the next one? Since we're already an hour and a quarter into this. First part about ICRP. These are all narrative descriptions. You can Google it and you can find these answers straightforward. It was in the report. The video you saw with Chris Clements. The three principles: justification, optimization, limitation. And then the situations are occupational, public, or medical. And then you can make up any examples you want of how you apply the principles to a situation. Okay. Next question we had, the computation question is: a worker is working in a nuclear plant or a nuclear facility, has a point source of cobalt-60 that's 10 millicuries in activity, located 5 meters away. Now, on the original problem, there was a hint that says we figured out what the air karma rate is in a homework in one of our classes. And so you can use that, just like I used the gamma factor, the gamma constant. When I did one of my problems, in this case, they're hinting that you should use the gamma constant for cobalt-60. So I use the value that is hinted that we derived. This is milligray per megabecquerel per hour. Actually, it's per second, I think. But let me see what it tells me here what it is. Oh, it was microgray per hour. That was what we calculated. So I'm glad I didn't make a mistake. Microgray per hour per megabecquerel. I have 10 millicuries, which is the same as 370 megabecquerels. So I did my conversion here to go what the activity is in megabecquerels to make those cancel out. And I get a dose rate at a distance of 1 meter. So the gamma constant is for dose rate at a distance of 1 meter. I'm told he's 10 meters away. No, 5 meters away. 5 meters away. So I use the inverse square law to figure out what the dose rate would be at 5 meters. So I'm dividing by the distance in meters squared. That's where 5 squared is 25. And I find out what the dose rate is at 5 meters. 46 micrograys per hour. Now the person works full time. So I take my dose rate and he works 2,000 hours. And that multiplies out to 91.2 mellagray because, or millisieverts, because the quality factor is 1 for photons. The person was exposed to other, had other exposures. What are the doses for those? We just did a problem like this last time. We had an absorbed dose. We want to know what the equivalent dose is. We multiply by the quality factor. Lungs and alpha is one that has a quality factor of 20. For betas and gammas, they stay the same. The equivalent dose is equal to the absorbed dose. Quality factor is 1. The one that changed is quality factor of 20 for lungs. So 20 times 0.005 is equal to 0.1. For bone surface, the quality factor is 20. So 0.1 for and times 20 is 0.01 times 20 is 0.2. And then the whole body, so all organs are, it's thermal neutron, 0.025 EV energy is thermal neutron. So I go back to my NRC. I think the radiation weight, the quality factors here. Thermal neutrons right on top. It specifically says thermal. 0.025 EV is 2.5 to the 7 minus 8 MeV, and the quality factor is 2. So I go back to my homework problem and I put in a quality factor of 2, twice as much as that. Multiply again by the tissue weighting factors that are applicable. So I use those and multiply them times the equivalent dose to get the effective dose contributions. Notice that I have for the lens of the eye, the effective dose is 0. It does not contribute to the effective dose. Quirk in the rules of the NRC. Skin doesn't contribute either. Okay. Add all that up, and I also have to add up the external exposure that he got, the 0.091 sieverts from the external dose, plus all these internal doses, and I add it all up, and he got 0.134 sieverts. This is effective dose equivalent in the NRC world. That would be 13 rem effective dose. It's above the limit. So the next question was, is it in compliance with the rules? It's above the standard for workers. So it's a problem. Then it says, how could you reduce the worker's dose? And so this is where creativity comes in. One way to reduce a dose is to move the workstation or to move the source and use distance as a way. But suppose that's not possible. Suppose this source is got to be there. It's a pump or some component that can't just be moved away. Then and the workstation can't be moved because he's working, in some location. Then the alternative, you have time, distance, or shielding. If we can't reduce time, we can't increase the distance he is from the source, then we can use shielding. There might be things you could do to reduce all these other exposures, right? You might wear a respirator if these are from internal exposures. However, they're only contributing a small fraction compared to the external exposure. So these all together add up to 0.04, and the external exposure is 0.09. So this already exceeds the standards. This is already 9 rem from the external exposure. So you've got to do something to reduce the external exposure, even if you do something to reduce the internal exposure independently. And so I said, I calculated that we have to reduce how much exposure is due to how much we have to reduce it. So we have this 0.134, right? And we need to reduce this down to his total exposure to 5 rem. If 4 rem is due to the internal exposures and they can't be reduced, and we have to get 5 rem total, that leaves less than 1 rem from that external exposure. It's 0.68 rem. Okay, that's how much that external exposure has to be, because this dose from all these can't, assuming they can't be reduced, but we have to reduce it enough to get the overall total below 5. So we're at 91. We want to rem. We want to get to 6.8 rem. That means you have to reduce it by a factor of 13. So if I were going to add shielding, I'd add a 10th value layer of whatever material. We're going to get into external exposure reduction in the next lecture, but just as a preview of that, and that's why I didn't calculate it all here. It's a coming thing. I would use a 10th value layer that reduces the radiation exposure by a 10th. I would add another half value layer. Instead of reducing it by 13, I'd reduce it by a factor of 20, a 10th value layer and a half value layer, and that gives me a little bit of margin of safety. And it's also probably a LARA. Okay? And then I start looking at what can I do to reduce these other exposures. How the heck do they all happen? Okay. Let's do now. We did not do a homework problem for this because it was the last lecture before the exam. And so we were supposed to be taking the exam, but I'm going to do an example problem from the lecture on radioactive measurement radiation. The second section was on statistics. That's one that you can do calculation problems. And the first one that would normally has been assigned in the past is explain all those regions on a gas filled detector. Explain what the recombination region is, explain what the ionization region is, what the proportional region is, what the Geiger region is, and how those different regions produce different kinds of detectors. That's just a qualitative description that basically covers probably half of the lecture. So that would have been a question you would have asked. You would have gone through the lecture. You would have thought all those things out and written them down. This is an important part of how gas-filled detectors operate. Is an important part, an important tool for health physicists, an important thing to understand. I'll just tell you that. But I'm going to do one with a calculation kind of problem that builds off of what we discussed there. And so this gives an example of a problem where someone does a wipe test and it counts it. And they want to see what the activity, what the contamination is in the lab. When they counted their wipe sample, they had 3,500 counts in 15 minutes. The background rate that was counted was 400 counts in 7 minutes. And the question is, what's the net background or the net activity? Well, you calculate the count rate for the sample. 3,500 counts in 15 minutes is 233 counts per minute. The background is 400 counts in 7 minutes. That's 57 counts per minute. The net count rate is just the count rate of the sample minus the count rate of the background. It's very straightforward. The question it asked it then is, what's the standard deviation of this count, of this net count? It's the standard deviation. So the way we do that is the variance, which is the standard deviation squared, is the count rate divided by the count time. So it's the count rate was 233 for the sample. The count time was 15 minutes. So it's 233 divided by 15 minutes. The background variance was 57 counts divided by 7 minutes. So it gets 23.7. The standard deviation is the square root of the background. So I take the square root of 23.7, I get 5. So I have 233 counts per minute plus or minus 5 counts per minute. Okay. I'm just trying to give an example here. It's going fast because I'm not using the calculator to push the buttons, but I want to show you the concepts in case you need to do this again at some point. So the another thing that was talked about in the lecture was the optimal count time. The formula for how we split the sample counting and the background counting is we take the ratio of the times is equal to the square root of the ratio of the count rates. So the gross count time divided by the background count time is optimal if the gross count rate 23.3 or 233.3 divided by the background count rate 57.1. Square root of that is equal to that ratio. So if you look at the square root of this ratio, it's 2.02. So that tells me that the gross counts, the time for the gross counts, it should be twice as big as the time for the background counts. Now the problem tells me I have a total time of 20 minutes to do this in. So if the total is 20 minutes and the background rate is 2 times the sample counting rate is the time is twice the background counting time, then the total of the sample counting time plus the background counting time is 3 times the background time. I just added this for TG plus TB. It came to 3.02 TB. Is this all clear? The math for this? And that's equal to 20 minutes. So it's a 2-to-1 split. So I end up with 10 minutes. 20 over 2 is 10 minutes. Wait a minute. Oh, this should be 3.02. I did a typo. So 20 divided by 3.02. It should be 6.6 minutes, not 9 minutes. 6.6 minutes for the background, and that would be 13.4 minutes for the sample. Okay. Okay, so I need to correct this before I post it. Then it tells me in the problem that I have an overall counting efficiency of 25%. That is 20, there are 0.25 counts for every disintegration. So activity is the count rate divided by that efficiency. My net count rate was 176 divided by the 0.25 efficiency. Tells me that there are 105 DPM decays per minute. There was 176. No, it's 176 times 4. Again, I have a typo. It's 704, not 104. That's 704. I couldn't read my own handwriting. 704 DPM and 704 DPM. Convert that to decays per second. 7, 4, 8 times 60 is 42,000 decays per, no. It's divided by 60. There are 11 counts per second, 12 counts per second. And converting that to then convert that to activity. The 12 becquerel is going to be is 3 nanocuries. Does that make sense? No, it doesn't make sense. It's 708 DPM, 704.8 times would be 11.4 becquerel, not kilobecquerel. I multiplied instead of divided. So it's 11.4 kilobecquerel, and then you can transfer, or 11.4 becquerel, and then you can convert it to microcuries. This should be microcuries. So I got a lot of typos on here. The next question was that the geometric factor, and let me show you what we had there for our remind you of what we did with that. We had the geometric factor is how much of the solid angle is intercepted by the detector. Here's the formula. We have a 5 centimeter diameter detector 15 centimeters away. So we just simply use this formula. And that's what I did here. I'm going to correct all these other mistakes in the counting rate, but I just figure out what the solid angle is and that find out what fraction that is of the 4 pi solid angle. It's 0.34. So we have 34% of our efficiency is just from geometric factors, and we end up with 25% overall efficiency. We're not losing many other counts to anything else besides geometry then. Okay. So I will put this, I'll fix this, my arithmetic here, and then I'll put that in the contents with the, put all these online that I've done. That'll give you a chance to go over it. To go over these problems, I'll put them in with the lectures or the homeworks that they correspond to, and give you a chance to study. Then we can come back on Thursday. We'll go over the broader topic, not just these computations of everything that's been covered in these units, and you'll be ready for your test. Okay, you'll have a week from after Thursday. You'll have a week to get it done. Gives you weekend time, weekdays times, plenty of opportunities. What are your questions for me?
I think you've answered all my questions. I really struggled on the last question in unit 7. So thank you for going over
Okay.
that. It's much more
It makes
clear.
sense.
It did, yeah.
The reason I'm doing this is I want to help people see the logic behind what we're doing, because then it makes it easier to set up a problem. It doesn't work well to just look through slides and find a formula. Sometimes that leads to success. Sometimes it leads to failure. Okay, any other questions I can help you all with? Don't hesitate to email me, whether it's about questions about the material, whether it's about how to do these problems, how to do anything else. Be happy to spend time working with you on it. Okay.
Sounds good.
Okay, thanks for taking time to go over this. And those of you who are seeing this after the fact, I appreciate you stopping by either Panopto or YouTube to see these videos. Have a great time.
Appreciate your time too. Thank you.
Bye-bye.
See you later.